So let's look at how you can find the number of signals in an NMR spectrum for a given compound. Basically, NMR spectrum displays a signal intensity on the y-axis against the frequency or the chemical shift on the x-axis. The x-axis has two main parts. We have the region of higher frequency and the region of lower frequency. The region of the higher frequency, which is at the left side where the arrow shows here, is called the downfield. Then that of the lower frequency at the right side here is called the upfield. Now the upfield here is displayed by nucleus or species with higher electron density. And downfield here is displayed by nucleus with a lower electron density. So here, if the nucleus has a lot of electrons around it, it is going to display electron here. So more electrons means higher electron density. And that nucleus is said to be shielded. It is shielded in the sense that the higher electrons around the nucleus shield away an external magnetic field from the nucleus. So shielded nucleus displays a signal at the upfield, whereas the shielded nucleus displays signal at the downfield. The number of signals displayed by an NMR spectrum for a given compound, let's say this compound, depicts the number of different environments for a proton in this case. So here, this one is an NMR spectrum for a proton NMR. So how many environments for protons or hydrogen in this compound corresponds to the number of signals displayed by the spectrum. Then the intensity, that is the height of the signal, corresponds to how many nuclei or how many protons contribute to a given signal. That is what we call the integration number. So integration number is the number of nuclei or the protons in this case that contributes to a particular signal in an NMR spectrum. Now let's see how we can correspond the protons here to the given signal here. If I've been given a compound and they ask you how many signals can that compound display in an NMR spectrum, it is equivalent to how many chemical environments are present in that compound. So let's say this one is a proton NMR spectrum. We have this compound. The number of signals displayed by this compound is 5. So here there are 5 peaks on this NMR spectrum, which indicate that we have 5 different environments for protons. That is, we have 5 different types of protons or 5 different electronic or chemical environment for protons. The chemical environment corresponds to the electron density around that nucleus, or let's say that proton, in this case the hydrogen. So if a nucleus is more closer to an electron withdrawing, like let's say an oxygen, that nucleus is always having a lesser electron density. In that case, it is likely to display a signal at downfield. That is where we display a signal with species with less electron density. So here, let's see the number of signals that this compound can display. We have 5 signals here. That means we have to have 5 different chemical environments for this compound. So for the chemical environment, we have the protons around this carbon to be in one environment. This proton and this proton, that's the TT, are also in one distinct chemical environment. That is, their electron densities are the same. This one and that one are also in one distinct chemical environment. Then this one in one distinct chemical environment. Then this one also in one distinct chemical environment. So here we have 5 different chemical environments for this compound. Now the 5 different environment means that this signal is going to, or this spectrum is going to display 5 different signals for the different environment of proton or hydrogen in this compound. Now the positions of the signals in the spectrum corresponds to the electron density that nucleus or that proton carries. So let's look at this case. The signal D, as seen here, the D here, we see it is the most downfield. If the D is the most downfield, then it means that the D is having the least electron density, followed by the C, before the B, before the A, before the E, then the A. So the species with the least electron density always displays a signal downfield. Then that with a higher electron density displays a signal upfield. If a species has a lot of, let's say, least electron density, we see that species is deshielded. That is, it deshields the nucleus from the external magnetic field. Then if it has a higher density of electron, it shields the nucleus from the external magnetic field. So nucleus with a lot of electrons are what we classify as a shielded nucleus, and that with less electron are what we call the deshielded nucleus. And shielded nucleus always display a species upfield, that is a region of lower frequency. Then the deshielded one displays a spectrum downfield, that is region of lower or higher electron frequency. The next thing to look at is to call off here is what we call a splitting pattern. Let's look at these compounds. So the splitting pattern is how the signals can split. Basically, if a nucleus displays a signal in an NMR spectrum, the number of adjacent nucleus around it, that is on the next carbon that holds that nucleus, can split. It can split because their magnetic field can interact. So the interaction between the magnetic fields of an adjacent non-equivalent nuclei is what we call the coupling, and the coupling can lead to splitting, which is the division of the NMR signal into, let's say, 2 or more lines. If I have this nuclei can be splitted, or the signal for this nuclei can be splitted if it has the nuclei on the adjacent carbon here. So let's say if this carbon has a nuclei which is just hydrogen like this, the number of nuclei here can split the signal displayed by the nuclei E. The number of divisions for particular signals given by a rule called the n+1 rule, where the n represents the number of adjacent nuclei. Then the 1 itself is the signal displayed by the signal by the nucleus of interest. Let's take proton D here. This proton D has a nucleus C on the adjacent carbon. So with this compound, the D and the D here, this one and this one all will display one signal. The nucleus on the adjacent carbon of the carbon that holds the D is the C and the C here. So since this D and D will all display one signal, the number of the carbons, or let's say the number of hydrogens on the adjacent carbon, is just this one and this one. So how many lines can the D have? That is the splitting pattern of the D. It is the n+1 rule. So here it is n. The n stands for the number of the adjacent protons in this case. So we have 2 of that. So it becomes 2 plus 3. 2 plus 1. Which when add, we are going to get 3. So here 2 plus 1 is what? 3. This 3 is the number of subdivisions that we can get if the adjacent nucleus split the signal displayed by D. If you have 3 subsignals, we call it triplet. If you have 2, we call it doublet. If you have just 1, we call it singlet. And if you have 4, we call it quartet. If you have 5, we call it quintet. If you have 6, we call it sextet. And if you have 7, we call it septet. So when they ask you for the splitting pattern of, let's say, this E, the E here, this E is splitted by no adjacent hydrogen. So the signal displayed by the E is singlet. The one displayed by the D here is of course triplet. If you have A, this A has a signal plus 2 adjacent hydrogen, triplet. If they ask you for that of B, this B has just one signal plus 3 adjacent hydrogen. So it's going to be 1 plus 3, which is 4. Going to give you 4 sub signals. We call quintet. If it is 5, we call it if it is 4, we call it quintet. If it's 4, you call it quartet, and if it's 5, you call it quintet. So the splitting pattern gives an information about the number of adjacent hydrogens on a given, or let's say that split a given signal. Let's come down here. Now we have this spectrum, and they are asking us which of the compounds below best matches the following proton NMR spectrum. The integration values are indicated next to their corresponding signals. So as I said earlier, the integration values corresponds to the number of nuclei or protons that add up or contribute to the particular signal. Let's see here. The next one, the first one, we have this 8. This is the second one, the third one, and the fourth one. So here, this compound, this spectrum is that of a compound that can display 4 signals for a particular compound, of which one is singlet, one is triplet. We can have here sextet and also a triplet again. So which of these compounds best corresponds to this spectrum? The first thing to do is count the number of signals that each of these compounds can display in a proton NMR. So if you look here, you can see this one has an environment here, 1, 2, 3, and 4. So there are 4 different environments for this compound A. That means this one is a candidate for this spectrum. Now let's look here. This compound is having 1 nucleus here, 2, 3, and 4. This one too can be a candidate for this spectrum. If you look here, we have 1 nucleus, 2 here, 3 here, and 4 here. So this one too can have this spectrum. Looking here, we have 1 here, we have nucleus here, we have nucleus here, nucleus. The nucleus is the nucleus of the protons, not of the carbons. Nucleus of the protons, not of the carbons. So let's look at it well. So we have 4 signals for this one too. The signals correspond to the number of different chemical environments we have for that particular compound. Looking at this one too, we have 1, and this one is here, 2 here. Now this one, the ones at the terminal, which is this one and this one, are the same. So this and this will display this one signal. This is 2 and 3. So it means this one is not even a candidate of this spectrum. Now let's take them one by one and see the splitting patterns and the integration values. Let's take the B first. For the B, it has this one to be singlet. This one too will be singlet because it has no hydrogen on the adjacent atom, what is here, the oxygen. Okay, it has 1 doublet here. So the splitting pattern of this carbon, the hydrogens on this carbon, is doublet because it's going to be here 1 here, and the N, which is the number of hydrogens on the adjacent atom, is what? 1 here. So it's going to be 1 plus 1, which is 2 doublet, but there's no doublet here. If you look at this one too, we have this one as 1 split by 3 hydrogens at the terminal, so we have 4 quartet, but there is no quartet here. So this one is not a candidate for this because in this compound we have a doublet here, but there is no doublet here. We have a quartet here, but there's no quartet here. Looking at the A, the C, and the D, let's look at it well. The A has a singlet. This hydrogen is a singlet because there is no adjacent hydrogen on the next atom here. Let's see. Yes, singlet. Okay, this singlet H. There is H here on this adjacent atom. There are 2 of that. So the splitting pattern of this hydrogen is this 2 plus the 1, which is triplet possible. The splitting pattern of this position itself is splitted by this side, which is 1, and the 2 here, which is 3. So it is going to be 3 here and 2 here, plus this 1 plus the 1 itself here, for quartet. So we have no quartet here. There is no quartet here. So this one too is possibly not a candidate for this, because this compound has a quartet. The splitting pattern of this hydrogen is quartet, because this one can be splitted by the hydrogens on the adjacent atom. At the left side, the adjacent atom is on the oxygen, which is what? Hydrogen. So here 1 hydrogen here, then 2 hydrogens here. So the 2 plus the 1 plus the 1 as the n plus 1 rule, where the n is the number of the adjacent hydrogens. The number of n in this case for this particular environment is 3. That is this one and this 2, giving you what? A quartet. There is no quartet here. So this one is not a possible candidate for the spectrum. Now if you look at C and D, C and D, which of these best matches the spectrum? Let's look at it well. For the C, it has 1 hydrogen here on this carbon. On this carbon, there's a hydrogen here. This hydrogen, the splitting pattern of this hydrogen is the number of adjacent hydrogens on the number of hydrogens on the adjacent carbon. So there's hydrogens here that can split the spectrum by this hydrogen. So how many? We have 2 here. So that 2 plus this 1 is what? 3. Is what? 3. So triplet. The splitting pattern for this hydrogen alone is triplet, because it is splitted by the 2 hydrogens here. So the n plus 1 rule, the n in this case is what? 2. So we have 2 plus 1. Therefore, the splitting pattern of this hydrogen itself is triplet. We have triplet splitting pattern here. Let's look at that of this center alone too. For this center alone, the hydrogens here, its splitting pattern, we have 1 here, then we have also 2 here. So we have the n in this case is what? Is 3. So 3 plus 1 in this case is 4, which is quintet. Quartet, but there is no quartet splitting pattern here. There is no quartet splitting pattern here. So this one too is not a possible candidate of this spectrum. Therefore, the D is the correct one. Let's test for the D. We have the splitting pattern. Let's say we have this one. The atom holding the hydrogen is oxygen. The next atom to the oxygen is what? Carbon here. And this carbon has no hydrogen, which is adjacent, and can split this. So the splitting pattern of this hydrogen on the oxygen is what? Singlet, because the next atom to the oxygen is what? Carbon, and this carbon holds no hydrogen to split the spectrum displayed by this hydrogen. So for this hydrogen, its splitting pattern is singlet. If I come here, for this particular center, the hydrogens here, which are 2, the splitting pattern of these hydrogens is n plus 1. The n is the number of the adjacent hydrogens, which is what? 2 here. So it's going to be 2 plus 1, which is 3. Triplet. We have possible triplet here. The next one is the splitting pattern of this one alone, this one proper. This one is split by the hydrogens here and the 3 hydrogens here. So we have 3, 2 here, which is 5, plus 1, which is 6. A possible sextet signal. Then the terminal one is, of course, we have 3 at the end. So we have 1 plus 2 triplet. So in this compound, we have 1 triplet. 2 triplets, 1 singlet, and 1 sextet. So meaning this compound is the right candidate for this spectrum. You can also look at the integration number. This indication means that one hydrogen is given a value of 8. So here, the integration value, which is the most downfall of this one, is 8. The next one is this one, which is triplet to this. The next one is this, which is sextet, as shown here. Then the last one is also what? Triplet. So this compound is the right candidate for this spectrum. Now let's look at these compounds here. We are just going to run through them. If they ask us to show the number of signals that these compounds can display, how can we do it then? We're going to just rush through fast. Then we can end the video. This compound is a typical symmetrical compound. There's a hydrogen here, a hydrogen here. That can give you one signal each because they are in the same chemical environment. There are 3 hydrogens here, 3 hydrogens here. So the hydrogen here and the ones here can all give you one signal. Then the ones here, the ones here can also give you one signal. So this compound can give you 2 signals for proton NMR. For proton NMR. Now let's say I forget if they ask for carbon-13 NMR, because carbon-13 also has an odd number of nucleons and can be stated with an NMR. So for carbon-13, that one also corresponds to the number of carbon environments we have this in this compound. For the carbon environment, we have also this one and this one, then this one and this one. So 2 signals for carbon-13 NMR for this compound, then 2 signals for proton NMR for this compound. Let's look at the B, the regions or different positions for hydrogen. We have the N here, we have here, and here. So this one shows 3 signals for proton NMR. Then for carbon, we have here, 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 and here, 4 signals for carbon NMR. The next one for proton here, this one, and this one, and this one, and this one will all display 1 signal. So these 4 regions can all display 1 signal. Then this side and this side can also display 1 signal. Then this one too, as for proton NMR. So this compound can display 3 signals for proton NMR. Then of course 1, 2 here, 2 signals for carbon-13 NMR. So for carbon-13, the carbon here and the carbon here will give you 1 signal. Then the carbons at the terminals will also give you 1 signal. So 3 signals for this compound for proton NMR and 2 signals for carbon-13 NMR. Let's come to this compound too. For this compound, this region and this region are the same. This region and this region are the same. Then you have here too. So 2 hydrogens or 3 different environments for hydrogens. So we have 3 signals for proton NMR. Then for the carbon-13, you can have of course 1 here, 2 here, this and this will be 3, this and this will be 4, then here will be 5. So we have 5 signals for carbon-13 NMR, but only 1, 2, 3 signals for proton NMR. This carbon has no hydrogen, this one has no hydrogen, so it has no signal for hydrogen. Let's come to E. For the E, we have this side, this side, this side being the same, this side being different with no hydrogen. This one has no hydrogen. 1 hydrogen here and 3 hydrogens here. So this E can display 3 signals. That is the ones at the terminals here, here, and here as 1, here as 1, then here as 1. So the E displays 3 signals for proton NMR, and for the carbon-13 you have 1, 2, 3, and 4 signals for carbon-13. We have more complex ones here like this. This one you have 1, 2. So here this one will display 1 signal. Then you have another proton here, 2, then 3 signals for proton NMR, then 1, 2, just 2 signals for carbon-13 NMR. Let's look at the H here. It has 1, 2, 3. So here we have 3 regions for protons, and there's one here which is what 4. So this compound can display 4 signals for proton NMR. And for carbon 13, we have the ones at the terminal, this one and this one and this one, all display 1. Then we have 2, we have 3, we have 4, we have 5, we have 6. So 6 signals for carbon 13 NMR. This carbon, of course, compound, of course, will display just one signal for proton NMR. Because this side, this side, this side, and that side are all the same. So this one, there's one and only one signal for both carbon 13 and proton NMR. Let's look at this one here. The hydrogen here is one environment. This one and this one is another environment too. This one is another environment. This one is another. So we have 4 signals for this for proton NMR, and for carbon 13 we have 1, 2, 3, and also 4 signals for also carbon 13 NMR. So these are some examples that you can go ahead and try. So try these questions and drop your answers at the comment section. So what do you think of A? If A is 3, if B is 4, or if it is 6, just write L, or let's say key, and drop the number of signals you think the answer is at the comment section. If you have any questions, you can drop at the comment section, or suggestion, you can drop at the comment section, so we can all look at that. Let me just randomly pick some of them and do it. So let's take the middle ones, the benzene derivatives. I'm going to do the benzene derivatives here, then the rest, this side and this side. You just try your hands on and drop your answer at the comment section. Let's look at F. So for benzene, all the hydrogens around them is the same. That's for benzene. So for benzene structure, it displays only one signal for proton NMR and one signal for carbon 13 NMR. Let's look at the G. There's one environment here. This side and this side are the same. This side and this side are the same, and this side too is independent. So this one, there's 4 signals for proton environment, for proton NMR, and for carbon 13 you have 1, you have 2, we have 3, 4, we have 4, then 5 signals for carbon 13 NMR, 4 signals for proton, and 1, 2, 3, 4, 5 signals for carbon 13. Let's look at the H. We have this environment as 1. This one and this one are the same. Oh, sorry, they are not the same. Sorry. This side as 1. Let me erase it so you can see it clear. Okay. For this one environment is this one. One environment is the proton on this carbon. One other environment is this one, and this other environment is this one. Then the other environment is this. So this compound can display 1, 2, 3, 4, 5 signals for proton and NMR. Here, the chlorine and the methyl, they're not the same. That means that these carbons here will all have different electron densities. So we say they are all in different chemical environment. Actually, they are the same, so it almost confused me. So here we have 1, we have 2, 3, and 4, as well as the one on this carbon. So 5 signals for proton NMR. Then for carbon 13, we can have 1 here, can have 2 here, can have 3, can have 4, can have 5, 6, and 7. So this compound displays about 7 signals for carbon 13. 1, 2, 3, 4, 5, 6, then this one 7 signals for carbon 13 NMR. Let's look at the I. For the I, this one and this one are the same, so there is no hydrogen on the carbons with the bromine. So we have 1, this one and this one 2, and this one 3. So 3 signals for proton NMR. Then when we come here, we have 1, we have 2, 3, 4, and this one 5, and 6. So this one can display about 6 signals for proton NMR. That's for the benzene derivatives. Try your hands on this one, that is A to E, then from also K to O, and drop your answers at the comment section. This is enough tutorials. Don't forget to like and subscribe after watching so you can receive every kind of update from this channel. Thank you.